Hello, everyone. So today we have the last lecture before our first exam. So congratulations, you've made it halfway through the semester with exams at least. Today it shouldn't be too bad, I don't think. We're just going to talk about logarithmic and exponential functions, and taking the derivatives of those. And for the most part, I don't think it's very difficult. There's just a pretty easy formula, and it's chain rule, which we should be pretty good at by now. And then we will talk about something called logarithmic differentiation, which is just a fun technique. Well, I think it's fun, but it's a technique that's useful when differentiation using our typical techniques is not possible. All right, so let's go ahead and first take a look at the natural exponential function. So I don't necessarily care if we call this e of x or f of x or anything, but let's consider e to the x, so the natural exponential function. Then the derivative of e to the x is just e to the x. And so what that actually means in terms of slope is that if you consider the slope at any given point, that's also the y value at that point. And so no matter how many derivatives you take of e to the x, you're just going to get e to the x. So the function is its own derivative. Now that's not the case when you have something other than x in your exponent. So that's something that I definitely want to make note of. A lot of times what we'll see is students will look at a function such as e to the 3x, and they'll say the derivative is just e to the 3x. And while that is part of the derivative, that is not the whole derivative because our exponent is not just plain old x. So this is the first definition, but I more so care about this guy right here. So it says if you have e to the g of x, where g of x is something other than just plain old x, then your derivative is going to be some form of chain rule. So it says you keep e to the g of x. So this is similar to like trig when we were dealing with trig. So if you were taking the derivative of sine of some function, you would leave that function inside of your sine. When you take the derivative of it, it would become cosine. And then you would multiply by the derivative of that thing outside. So it's very, very similar here, except now we're dealing with e. So you're going to leave the function and then just multiply by the derivative of whatever it is in your exponent. So it's very important that we remember this extra step here. All right, so let's go ahead and try an example. I don't think that these are too bad right here. So f of x is e to the tangent of 2x. Let's find f prime of x. So f prime of x is, well, since this is an e function, we know our derivative is going to have this exact function in it. So we will have e to the tangent of 2x in our function. We can always just rewrite the original function first. All right, so you get some points just by rewriting your original function. But now we have to consider that this exponent is something other than just x. So what we have to do is we multiply by the derivative of this function. And so if you'd like, we can just go ahead and multiply by the derivative, but we can also say, let's take the derivative of the exponents. All right, so this is notation saying we want to take the derivative of this exponent. And when we do that, all right, let's rewrite this again. Well, we know the derivative of tangent is secant squared, but we have something, again, other than just x inside of our argument. So this is another case where we're going to have to use a chain rule. So we always leave what's in the argument without touching it. We don't want to modify it whatsoever. The place where we do want to consider what's happening is going to be outside, where we multiply by the derivative of what's inside. So the derivative of this 2x is just going to be times 2. And so our derivative of e to the tangent of 2x is two chain rules. Technically, the chain rule happens when you take the derivative of your exponent, but then it also happens when you take the derivative of this argument. And so this is the answer. You can move the 2 over in front of the e if you'd like to, but this is an absolutely fine answer. All right, now what about if we have a quotient rule instead? Technically, if you'd like, if you prefer product rule, you can make this into a product rule by taking this x to the 1 and bringing it up and making it x to the negative 1. But we're just going to apply this as a quotient rule just to get some practice with quotient rule. So we remember quotient rule says the derivative is low d high minus high d low over low squared. All right, so let's go ahead and compute that derivative. So find the derivative of y. So the derivative of y is y prime equals low, which is x, d high. So our exponent is e to the x squared. So I'm going to pull it off to the side just because, again, this is the first time we're seeing this. So the derivative of e to the x squared, what is it? Well, first of all, we rewrite our e. So it is just e to the x squared. But because it's not just plain old x in our exponent, we have to multiply by the derivative of our exponent. So the derivative of x squared is 2x. And so technically the derivative of e to the x squared is e to the x squared times 2x. And in fact, if you consider just e to the x, you're actually still applying the chain rule because the derivative of x is just 1. And so you're getting e to the x times 1. And so it is the same exact thing. It's just you're not necessarily thinking of it as a chain rule. All right. So anyway, back to the quotient rule, low d high, and we just said the derivative of the e to the x squared is this right here. So I can just rewrite that, e to the x squared times 2x minus high, so we can just rewrite the e to the x squared, d low. Well, the derivative of x is just 1, so I don't need to write that. All over low squared, which is x squared. And I don't need to put parentheses because that's just a regular x. And again, this is absolutely fine. If you would like to simplify in a way by multiplying this x by this x, you can. But you'd have to be very careful not to try to cancel it out with this down here because this e to the x squared term here does not have any x's. So that's why it's best to just leave it like this and you don't have any potential simplification errors. Now we can take a look at an application question. So on exams and stuff like that, we will not be allowed to use a calculator. Obviously on homework, like Lumen homework and stuff like that, there will be some questions that maybe do ask for like a decimal place, so you will be allowed to use a calculator in that sense. But it's encouraged not to use a calculator, and you're not allowed to use a calculator on the exam. So when we're looking for the answer for this, the answer will just be once we plug in the value, and we're going to leave it like that because e is an irrational number. E is similar to pi. It's approximately 2.717, and it kind of just goes on forever. It's just like pi is 3.1415, and that goes on forever and ever. All right. So a colony of mosquitoes has an initial population of 1,000. After T days, the population is given by this function right here. So it says A of T equals 1,000 e to the 0.3 t. I'm just rewriting it. Show that the ratio of the rate of change of the population A prime of T to the population A of T is constant. So we're looking for a ratio, but first we need to find A prime of T. So let's compute that. A prime of T equals, all right. In order for something to be constant, that means that when you find the ratio, it must just be an integer or a whole number. So let's compute this. For our derivative, we get, well, this 1,000 can stay out front because it's just a coefficient. And then we can take the derivative of e to the 0.3t. Obviously, since it's an e, we can just rewrite e to the 0.3t. But then because it's not just a t, so instead of an x, we'll say a plain old t, we do have to multiply by the derivative of that exponent. So the derivative of 0.3t is just going to be times 0.3. Now, in this case, because we are looking for a ratio, we're going to want to combine the 0.3 with the 1,000. So this is the same thing as saying 3/10 of 1,000, which is the same thing as 300 e to the 0.3 t. So now if we're looking for the ratio of the rate of change, which is a prime of t, to the population, which is a of t, we're looking for a prime of t to a of t. This is the ratio that they're asking us to set up. All right, well, we can just go ahead and actually plug in those values. We know what a prime of t is, and we know what a of t is because we computed a prime of t. So this is 300 e to the 0.3 t for a prime of t, and they gave us a of t. That's just 1,000 e to the 0.3 t. And if you notice, we have an e to the 0.3 t in the numerator and the denominator, which means that this term just cancels out. And so what we're actually left with is 300 over 1,000, or if you think about it, we can also cancel out a couple of the zeros and we get 3 over 10. We're trying to show that this is constant. 3 over 10 is a constant. Therefore, the ratio is constant. If you were asked to find, um, say, the rate of change after 4 days, all you'd have to do is find a prime of t and then plug in 4. So this is where you probably wouldn't want to plug it into a calculator because you'd get some crazy looking decimal. All right. So now we also have to talk about the natural log, because if you remember from pre-calc, we have this idea of inverses and functions that are inverses to be specific. And we have the natural exponential function e, which is the inverse of the natural logarithmic function ln. And so we have this fact that says ln of e is equal to 1. And that's what happens with inverses. To be an inverse means when you take the inverse of the function, you just get 1. So that's naturally why we want to talk about the natural logarithmic function at the same time that we talk about the natural exponential function. All right, so we are considering y equals ln x, and we want to find the derivative of this function. So this one does not behave at all like you would expect it to. So this is something that you're just going to kind of have to memorize. So if you have y equals ln x, then the derivative with respect to x is 1 over x. So the ln goes away and it becomes 1 over whatever it is you have in your argument. Again, this way I suggest maybe not focusing on quite so much, because most likely you're going to have something other than an x inside of your natural log. And if you only consider this rule right here, you're not going to be taking into account what happens when you have something other than an x. So let's consider this way. If g of x is just some differentiable function, which is positive because we know that inside of a natural log, the domain is just positive numbers. So we're going to consider h of x as the natural log of some function g of x. Then the derivative is given by this. So 1 over just the thing inside the parentheses. So we're getting rid of the natural log completely. 1 over the thing in the parentheses. But then because you've just rewritten the thing in the parentheses, we haven't really taken that into account. So we multiply by the derivative of that thing. So this is the proper definition of a natural log. All right, this is the way that we're going to be focusing on right here. So let's take a look at an example. All right, so it says f of x is the natural log of x cubed plus 3x minus 4. This is why we don't want to look at the first way, because if you look at the first way and you forget that x represents some general x, then you might say that the derivative of this is maybe 1 over just this value right here, instead of multiplying by the derivative of this and actually using the chain rule like we're supposed to. So the derivative rule says f prime of x equals 1 over the thing in the parentheses, this argument, which is x cubed plus 3x minus 4. But because this is something other than x, we have to consider that by multiplying by the derivative of that thing in the argument. So the derivative of x cubed is 3x squared. The derivative of plus 3x is plus 3, and the derivative of minus 4 is 0, so we won't write that. If you'd like, you can bring this into our numerator, so you can just multiply this right into the 1, but this is also fine as an answer. And it's just that simple for questions like that. There's nothing else that we have to do. 1 over the thing in the parentheses, multiply by the derivative of the thing in the parentheses. Now, of course, sometimes the thing in the parentheses isn't so nice. Sometimes it's something crazy like that. So let's go ahead and take a look at this. There are 2 ways that we may try to do this. So the first way is using the technique we just did there, which is do 1 over the thing in the parentheses and then multiply by the derivative of that thing. Now, the second thing is actually, again, a throwback to pre-calculus. It's using the properties of logarithms. And what they mean is by using log rules. I believe that we went over this on either the first or the second day. We kind of ran through the log rules real quick. So let's do another refresher of the log rules. In my opinion, using this method is easier. So we're going to split it up using log rules to begin with, and we're going to get a bunch of natural logs. And then we're going to take the derivative of each individual natural log so that it's easier than having to do a quotient rule, but this is a product rule inside of it. So you do a quotient rule with the product rule, and it just kind of becomes a mess, honestly. So here are the log rules. So the first one says that you can have, well, I'll rewrite it as a natural log, I guess, because that's what we will be using in this case right here. So if you have a natural log, this does go for a regular log log too. If you have the natural log of a to the b power, you can rewrite this as b times the natural log of a. The second log rule is if you have the natural log of a times b, you can rewrite this as the natural log of a plus the natural log of b. And so multiplication within a log turns into addition between two logs. And the third rule is that the natural log of a divided by b is equal to the natural log of a minus the natural log of b. So division inside of a log turns into subtraction between logs. So my suggestion will be to expand it in the best, furthest way possible, and then to take the derivative from there. So what we'll do, since we're expanding, we want to use 2 and 3 first, then 1 last. So there's no way of pulling out an exponent, especially if you look here at this 2, right? There's no way of pulling this 2 out when you have other things here, because you'd have to take a squared out of everything, but there's only one thing squared. So removing this exponent to be multiplication is the absolute last step. So we'll go ahead and deal with the multiplication and division first, and then if there's exponents, which we do have, we'll deal with that after. So let's go ahead and rewrite this first. I'll rewrite it first using the division rule. So this tells us that f of x equals the natural log of a being the entire numerator. So I'm going to say x squared sine of x minus the natural log of the entire denominator, which is 2x plus 1. And I do want to note, if you look here, these are the only 3 log rules. There's no rule that says if there's anything that we can do with addition. And in fact, there is nothing that we can do if you have addition or subtraction. Once you get there, unless there's something you can like factor nicely, you're stuck. There's nothing else you can do. So don't try to separate this in any way. All right, now you see here, you have multiplication between x squared and sine of x. So we can use rule number 2 that says multiplication inside of a log turns into addition between logs. And so we can say this is equal to the natural log of x squared plus the natural log of the sine of x. And then we can just kind of tag this natural log of 2x plus 1 onto the end of it. Now the last thing is we can apply this first rule, and that really only applies to this first part right here, the natural log of x squared. So we can pull the 2 out to the front, which turns into 2 times the natural log of x plus the natural log of the sine of x minus the natural log of 2x plus 1. All right, so again, we haven't necessarily done anything besides expand this log yet. So this is still just f of x, but we're looking to find the derivative. We're not looking to find the function expanded. That was a pre-calculus thing. And if you took pre-calculus and you were looking at this and you were like, why would I ever want to do this? This is where this might come in handy now. Because now if you're taking f prime of x, you're taking the derivative of 3 different logs, and it makes it so much easier. For example, the natural log of x we know is just 1 over x for its derivative times 2. So 1 over x times 2 is 2 over x. So f prime of x is 2 over x for the derivative of 2 times the natural log of x, which is already so much easier than trying to take the derivative of this thing, which is a quotient and a product and a mess. Plus, the natural log of this is 1 over the argument, which is the sine of x, times the derivative of sine, which is cosine of x. There's nothing inside of our x besides an x, or our argument besides an x, so we don't have to do anything with that. Again, we notice how much easier this is already just by using some log rules to expand our equation. Minus the natural log turns into 1 over the argument, which is 2x plus 1, and then we'll multiply by the derivative, which is just going to be 2 here. And that is your answer. This is going to give you a significantly easier answer than trying to do the derivative directly. So I suggest breaking this up if you see this as a question. And definitely remember your log rules. These will come in handy. All right. These I definitely have to mention. These are like the honorable mentions of the lecture. Honestly, these aren't used very much. I remember learning them when I took calculus many years ago, And I think I've used them maybe just a handful of times throughout all of my years of doing calculus, because it really doesn't have as many applications as we'd like. Natural logs and e's have a lot of applications in the real world, whereas regular logs are a little bit more specific to things. So, I'm obligated to give you these as formulas, and we will do maybe like two practice examples just so that you can see what they look like as derivatives, but I wouldn't expect to see very many of these just because it's not quite as intuitive and it's also not quite as useful just in practice. So I'm going to skip over the general rule because the more complicated rule takes care of the general rule as well. So if you have h of x, which is some log base b of some function inside of that, again, g of x has to be positive just because this is a log, then your derivative has this form. So it's g prime of x over g of x times the natural log of b, which is your base. If instead of starting with a log, you start with, we'll go down here, a base, so some number, not an e, maybe like a 5 or a 7, to some function, then your derivative looks like this. So the derivative is keep the function. So this works the same way as a natural exponential function, e, multiplied by the derivative of the exponent. But this is the kind of the extra part here where you have to consider what the base is. So you do ln times b. And this is actually the same idea for ln e, except that ln e is 1. And so this is kind of like the general rule. It works the same way for ln's with this because a natural log is just a regular log base e, but we don't really like to think about it like that a whole lot. Again, these really don't have as many applications as we would like for them to have necessarily. All right, so let's go ahead and just do a couple of practice. We're not going to do a whole lot with this. So here is a quotient. We're looking at 3 to the x, and we're going to need to find the derivative using the quotient rule. So we again remember that's a highlighter. We remember low d high minus high d low over low squared. Therefore, h prime of x equals low, which is 3 to the x plus 2, d high, but I'm going to again write, all right, what's the derivative of 3 to the x? So because we're looking at using the log rule that we just learned, which I will go back to it, using something to some exponent, you keep that thing, multiply by the derivative of the exponent, and then put ln of your base. So we're just going to use that right there. So the derivative says, keep this, multiply by the derivative of your exponent. That's just 1. We don't need to write that. And then do the natural log of your base, which is 3. So that's the derivative of 3 to the x. So therefore, low d high. So this is the derivative of the numerator, which is 3 to the x times the natural log of 3, minus high, which is your numerator, 3 to the x, d low. So the derivative of 3 to the x plus 2 is actually just considering the derivative of 3 to the x because the derivative of 2 is 0. And so the derivative of 3 to the x is, again, the same thing we just wrote here, 3 to the x ln 3, and that's all over the denominator squared, 3 to the x plus 2 quantity squared. Now, there is a very nice way of canceling some of these things out. Technically, if you distributed this 3 to the x and the 2 to this term here, you could cancel out the 3 to the x times the 3 to the x ln 3. But again, that's just not very necessary, especially given the rule that we're looking at. It does not feel very necessary. And there's not going to be a time when I ask you to simplify unless you're asked to find the equation of a tangent line where you actually have to plug in a number, or you're doing implicit differentiation where you do have to find dy over dx and you do have to move things around a little bit more. All right, now let's just take a look at a log. We will look at the equation of a tangent line just to get that in here. So for a log base something of something, let's go back to the rule. So it says if you have a log base b of g of x, that's g prime of x over g of x with the natural log of the base in the denominator. So let's use that. So that tells us that y prime equals, it says the derivative in the numerator of just the thing that's in the parentheses. So the derivative of 3x plus 1 is just 3 over And then it says you leave g of x in your denominator. So that's 3x plus 1. That's just the thing inside of your parentheses. And then you multiply by the natural log of your base, which is 2. That's it. We don't need to simplify this. In fact, we can't simplify this any further. This question doesn't have the scenario that I'm about to mention, but if you saw something like just the regular log of 3x plus 1, I will note that if no base is written, it is assumed to be 10. All right, so this is called a common logarithm. I'll rewrite that word, assumed. That doesn't look like the word assumed. That's called the common logarithm. If you don't see a base, it's 10. There is a base, and that's the base that we'll use. All right. Now we're getting to the last part. It's this idea of logarithmic differentiation. So this is using the idea of logs and the derivative of logs, specifically natural logs, to differentiate things that normally would be difficult or impossible to differentiate without. And we see that in a note here. We use this technique when our function does not satisfy any known rules. All right, so let's look at this strategy. So first, to differentiate using logarithmic differentiation, we take, I don't know why I keep using the eraser. You know, by the end of this course, I will remember to click the highlighter instead of the eraser, I promise. Take the natural log of both sides to obtain this equation. So if you're given y equals some function, you'll get ln y equals the ln of whatever it is that you have. So I'll highlight the important things. Take the natural log of both sides. Step 2, kind of what I mentioned earlier, what we want to do is we want to use the log laws to expand the log as much as possible. So expand it until you have things in your parentheses that cannot be expanded any further, because once you have that, it becomes significantly easier to actually differentiate. From there, you can differentiate both sides of the equation. But what you notice is here you have the natural log of y. And if you remember back to implicit differentiation, when we have a function applied to y, we have to consider that this is no longer y in terms of x. This is now an implicit function, not an explicit function. So this function here is an explicitly written function. This is an implicitly written function. And so when you take the derivative of the natural log of y, you do follow the log rules, which is 1 over y. But then when you multiply by the derivative of y, that's just dy dx. And so on the left, we will have 1 over y dy dx. And then on the right will just be whatever it is that you're looking at. Multiply both sides by y to solve for dy dx. So this is one of the more easy ways of doing implicit differentiation because there's only one step to get rid of your thing next to your dy dx. You don't have to factor, you don't have to do anything except for multiply by y. And the cool thing is that since we started with y equals, we had an explicitly written function from the beginning. And so similar to when we were talking about inverse functions, we can go ahead and just replace whatever we had for our y to have everything in terms of x's. So anywhere you see a y, substitute in the equation you're given. All right, let's go ahead and try an example. All right, so we see y equals 2x to the fourth plus 1 to the tangent of x. And so this is where you'd look at this, and even if you weren't told use logarithmic differentiation, you'd probably look at this and be like, what the heck is that? We can't distribute a tangent function. It's not like it's a squared or a cubed and there's a nice way of distributing it. This is a tangent. Tangent doesn't have a distribution. So we have to use something different. That different thing is going to be trying to get the tangent out of your exponent. But the only way of getting something out of an exponent is by using a logarithm. So that's why we're using logarithmic differentiation here. So first step is take the natural log of both sides. So we'll have ln y equals ln of 2x to the fourth plus 1 to the tangent of x. And I'm putting big parentheses around everything just to kind of make it a little bit more obvious. Now, step 2 says simplify this right-hand side as much as possible. Expand it. So because this here is addition, there's nothing that we can do. There's no multiplication or division, so we can't expand it like that. The only thing we can do is bring the exponent down to the front. And so I'll say that the natural log of y equals, I'm going to take this and I'm going to bring it right to the front of my function. If there was multiplication or division in here, I would do that first. So this becomes the tangent of x times the natural log of 2x to the fourth plus 1. Again, there's nothing we can do to simplify that at all. Now we differentiate. So the derivative of the natural log of y is 1 over y, but then the derivative of y is dy over dx equals, and the derivative of this is a product between two things, so we will use the product rule. We remember the product rule is either f prime g plus fg prime, or first derivative of the second plus second derivative of the first. Same exact thing. All right, I like this one. So here's my first, here's my second. All right, so first I'll rewrite tangent of x times the derivative of the second. So the derivative of a natural log is 1 over the thing in the parentheses, which is here 2x to the fourth plus 1. But then we have to multiply by the derivative of the thing in the parentheses. So the derivative of 2x to the fourth is 8x to the third, and the derivative of 1 is 0. So we can finish it off with that. So that's first times the derivative of the second plus second. We can just rewrite the natural log of 2x to the fourth plus 1 times the derivative of the first. Well, the derivative of tangent we know is secant squared of x. And then the derivative of x is 1, so we don't have to actually rewrite that. All right, so once we take the derivative, all we have to do is multiply by y to get dy dx by itself, and then we'll substitute y in to get our final answer. So dy dx equals, this is typically how I do it, y, and then I'll do big parenthesis, and I'll just rewrite literally everything. Tangent of x, I will bring this 8x cubed into the numerator here just to kind of condense it a little bit. So tangent of x times 8x cubed over 2x to the fourth plus 1 plus, and this I'm just going to leave, the natural log of 2x to the fourth plus 1 times secant squared of x. We know what y is. We know y is this thing right here, so we can say dy dx equals, rewrite y as 2x to the fourth plus 1 tangent of x, and then rewrite all of this again. So tangent of x, 8x to the third over 2x to the fourth plus 1, plus the natural log of 2x to the fourth plus 1 times secant squared of x. If I have enough parentheses, this should work. All right, and that's your final answer right here. All right, let's go ahead, and I believe we have one more to try, and then that will be it for the lecture, the last lecture before our first exam. All right, so this one is, again, crazy looking, and you definitely don't want to try to find the derivative of this using quotient rule. So this you don't have to use logarithmic differentiation for, because you notice this is just y equals, and this is just a regular old function. So you could use quotient rule if you wanted to, but if we think about it, this square root implies that there's a chain rule, but the x times that implies a product rule. This whole thing is a quotient rule, but the denominator here also has a product, but the sign cubed also implies a chain rule. I don't know how many things I just listed, but I promise you don't want to do all of those. So if you see something like absolutely crazy like that, maybe we want to use logarithmic differentiation just to simplify our lives a little bit. So let's go ahead and use logarithmic differentiation just to show that this makes it so much easier. So we'll take the natural log of both sides. Ln of y equals ln of x square root of 2x plus 1 over e to the x sine cubed of x. Okay, now we can use our log rules to simplify this. So we remember division inside of a log turns into subtraction between logs. So we'll do that one first. So we'll say the natural log, I'll say implies the natural log of y equals the natural log of the numerator, which is x times the square root of 2x plus 1, minus the natural log of the entire denominator, which is e to the x times sine cubed of x. Now we have a product within this log, and we have a product within this log. So products within logs turn into addition between logs. And so this implies that the natural log of y equals the natural log of x plus the natural log of the square root of 2x plus 1 minus, and now because we have a minus here and we're going to turn this into addition, we have to put parentheses here because we are now taking one term and making it into two, but we're still trying to subtract that entire thing. So we have to consider that when we're doing this. So minus the natural log of e to the x plus the natural log of sine cubed of x. Okay, I think I have enough parentheses. Now the last step is going to be dealing with our exponents. So the first thing that I want to note is a square root changes into a fractional exponent. So if you have the square root of x, we remember we have this rule that says we can rewrite it as x to the power over root. Well, we don't have it written here. So both of the numbers are implied. That means that this is an implied 1 and this is an implied 2. So this is 1 over 2. So that means that this square root here is actually an exponent of 1/2. So let's start rewriting this and we'll change it as we go. So the natural log of y equals the natural log of x. We can leave that plus. I can rewrite this square root as a fractional exponent, but once I do that, I can bring it to the front of my log. So I'm just going to do that. I'm going to write 1/2 natural log of, and then just the 2x plus 1. I will go ahead and distribute my minus and also take care of my exponents at the same time. Minus, I can take my x and bring it down, so x natural log of e, and then minus, again, so this is mathematical shorthand. I could have written this as sine of x cubed, so I can write this as minus 3 natural log of sine of x. The last thing that I want to note is the natural log of e is just 1, and so that actually just kind of cancels out. So we're left with just minus x. Now we have this, which is just the function where we've expanded it, and we can go ahead and take a derivative. And as you can see, this derivative is already going to be significantly easier than product with quotient with product with chain with more chain and more product. That just sounds like a nightmare. So let's take the derivative of this guy. Derivative of the natural log of y is 1 over y times the derivative of y, which is dy dx, equals the natural log of x is just 1 over x, derivative of x is 1, plus 1 over 2, natural log of 2x plus 1's derivative is times 1 over 2x plus 1 times the derivative of 2x plus 1, which is 2, minus x, so the derivative of minus x is just minus 1, minus 3, the derivative of the natural log of sine of x is times 1 over the sine of x, because we keep the thing that's in the parentheses and just put it in the denominator, but then we multiply by the derivative of the thing in the parentheses. So the derivative of sine is a positive cosine of x. All right, the last step is just going to be by multiplying y to the other side. And then after that, we'll substitute in what our y function was. So this implies that dy dx equals y times 1 over x plus 2 times 1/2 is just 1. So I'm going to cancel these guys out and just say that this is 1 over 2x plus 1 minus 1 minus, I'm going to bring the 3 and the cosine into the numerator. So 3 cosine of x, just to condense it a little bit, sine of x. So this isn't me necessarily changing it or trying to combine anything. It's just me rewriting my multiplication a little bit to just make it look a little bit more concise. All right, and then the last step is just to substitute in our original y. And so dy dx equals y. The original y is x times the square root of 2x plus 1 over e to the x sine cubed of x times this whole thing here. So this is 1 over x plus 1 over 2x plus 1 minus 3 cosine of x over sine of x. And this is your final answer. I do know it looks crazy, but I still promise you this was way, way easier than trying to actually do this by directly computing the derivative. All right. I do believe that this is the last, yep, this is the last slide for today. I will have some form of review sheets to give to you for before the test. So if you have any questions, let me know. And I will see you for the test.